All right, we are continuing our discussion on screws, bolts, and power screws. And now we are going to talk about the static stresses in screws and bolts and power screws. So this discussion applies to all of these. And the first one we'll talk about is simple to calculate, and that's just the shear stress. And that's the shear stress experienced in the cross-sectional area of the bolt. And it's just equal to the bolt torque times the distance from the neutral axis over J, which is a pull moment of inertia. And we already have the equation for that for rod, which is 16 times d over pi d cubed. And in this case, we just use d is the root diameter of the of the bolt or screw or power screw. It's important to note that some torque is lost in the collar in the case of power screws, or in contact friction in the case of your bolts and screws. So a reasonable assumption is that half of what we call the wrench torque, that would be the torque that we would measure at the wrench. A reasonable assumption is that half of the wrench torque makes it into the screw. And obviously, this would be highly dependent on friction. But the point is that, if we're putting a screw or bolt in to something, let's see if it's threaded, unthreaded, if we have a nut, we don't have a nut, or if it's a power screw. Let's say we have a torque wrench, or we have a wrench here that we're applying the load to. Let's say we have a socket that we're tightening a bolt. When this bolt comes in contact with the surface, the torque that we read up here is not going to be the same as the torque that is present here in the bolt on this plane. So this torque on the bolt is not going to be equal to the applied torque from the wrench, and that's because of this friction. And so a reasonable assumption is that at least half of the applied torque gets in there. And measurements have been done, and it's estimated that the torque wrench value versus the torque in the bolt is easily off by plus or minus 30%. So that's something to note. So assuming that we could accurately measure the torque that's applied to a bolt, we could get the shear stress in the bolt. Okay. We can also take a look at the axial load / stress, and this is just simply the Z component of that stress on the bolt, and we use the just the force over the area that's applied to the bolt, where area A is just the average of the pitch and root diameter, and we derived that earlier in a previous video. If we wanted to know the state of stress from these two, we can calculate that using the distortion energy theory, and we can find our equivalent stress is equal to the square root of this sigma Z squared plus 3 times the shear stress squared to get a estimate of the state of stress in the bolt. We also have what is called bearing stress. Okay, and the bearing stress is the stress that we would have. Let's say if we have a bolt, and that bolt, we have a clamped member here. This would be the clamped member, and we have a nut. Let's say this is our nut, and that nut is applying a compressive stress. Okay, so if we have this clamped member and we tighten this nut down against this clamped member, this is our clamped member, this is the nut, this is our bolt. Okay, and so when we clamp this clamped member down, we have this load, and this load is applied here through those threads and then up through here. Okay. So if this is the load P here from that clamping force, this is the same load that's experienced here, and this is a compressive load applied to the nut, from the nut on the screw or the threads, and this is called the bearing stress. And we can say that this is just the stress, that's this compressive stress, which is equal to the load P over the area, and in this case we can take the average area as pi d squared minus di squared, or we can just say pi d minus di, which would be the major diameter over the inner diameter over the load, times the thickness that is over. So if this is our nut thickness T, and it's applied through the threads, and we have so many threads per inch. Then we can take the pitch, which is our threads per inch, over the height of the bolt, T. So this is the, sorry, the height of the nut. This is the nut height. Okay, and this is our threads per inch. What is interesting to note is that if you look at the flow lines of stress here, from the clamped portion through the nut into the bolt, they don't have the same distance from the load, and what that means is that the load is not applied equally to the threads. And although it's fine for most cases, there's actually specialty nuts that are designed to redistribute this load. It also means that the stresses are not equal on each individual thread. And so there's, like I said, some specialty fasteners that can address that. But care has to be taken that the thread experiencing the greatest load doesn't strip out. So we can actually take a look at the stress, which is called the stripping stress, that would cause threads to be stripped. So nuts are typically weaker than bolts, and as such will often shear first. But obviously this depends on how many threads are engaged, which is a function of the thickness of the nut. For the Universal Thread Standard and ISO bolt geometries, we can take a look at the shear area, and that comes from, if you're looking at the, let me try that again, if you're UTS or ITO, if you're looking at the thread, oh goodness, if you're looking at the thread geometry of a thread and a nut, let's say that's your nut, that's your thread. So if we look at the geometry for the Universal Thread Standard or the ISO thread geometry, we can calculate the shear area from that thread geometry, and it turns out that that shear area is 0.75 times T, where T would be the bolt thickness, times pi d, so that would be the circumference, of the shear fracture surface. And if we choose this to be the major diameter, we can say that this is the shear area. And so we're effectively saying that this is the shear area if we have a nut and bolt or screw. What we're talking about is this cross-sectional area here. Okay, that would be the shear area. For the geometry of the standard thread, we can calculate this. So that's the shear area is 0.75 times T, and T would be the thickness of the nut. And then we can calculate the force in that nut to be pi d times 0.75 T times the ultimate strength and shear, the yield strength and shear. So we're calculating the stripping stress, or the stress that would occur, and that would occur to this because of this shear in that shear plane, and the shear plane happens across this shear area. So we can calculate the force, and that's the yield stress and shear. We can relate this because we know that the yield stress is about 58% of the that the yield and shear is about 58% of the yield stress. So we can rewrite this as pi d times 0.75 times 0.75 T times 0.58 SY. And then we can relate that to the force in the bolt, and we can say that this is the area of the bolt when in tension times the stress that causes it to yield. And if we use 90% of the diameter, we can say that this is pi times 0.9 d squared times sy. And if we equate these, we just say that the force of the nut is equal to the force in the bolt. And when these two are equal and they are at the max, at the yield strength of the material, then we can get an expression for the thickness, and we can say that, well, the thickness of the nut is about 0.47 times the diameter. So it turns out that the standard nut thickness is about it's approximately equal to about 7/8 the diameter, or 87 0.875 or 87.5% of the diameter. So it shows that the safety factor is about 1.86. So what this means is, if we want to design such that the bolt will not strip out, but instead the bolt would fail, then we'd have to have it would have to be threaded into either the nut or whatever it's threaded into 7/8 of the diameter at least. Alright, so we've covered the shear, axial, bearing, and stripping stresses, and now we need to talk about the proof loading of a bolt. Okay, so the proof load, or Fi, is the load just below the load that causes permanent deformation. Okay. So for some materials, this is going to be equal to the same as the 2% offset stress, but in general, it's a load that's just below the load that causes permanent deformation. So many applications suggest loading to the proof strength, or the proof load, and they often use proof strength or proof load, and the reason is that even though you're almost at the permanent deformation load of the bolt, you want to load to that proof strength, because if you have something that's, say, bolted together, let's say you have a nut and you have a bolt, the rationale is for many applications you won't get any more elongation in the bolt unless you have separation in the things that are bolted together. The other rationale is that if you load this bolt up and you load it to the proof, you're applying the maximum load between these plates here, and so you're increasing that normal force, which means that you're minimizing the tendency of the bolted joint to slide. Okay, so this is a big deal. And there's tables for the proof strength for various types of bolts and various SAE grades. So you can actually look it up. This is just a website that shows different grades. These are the SAE grades, and they give you the values for the proof strength. As you can see, it's slightly under the yield strength. And these SAE head markings, these is for US bolts, and they go in terms of class and or grade for the US specification, and the SAE grade is 1 through 8, and then the SAE class is the metric version, and it's 4.6 through 12.9. For the US bolts, you can actually look at the bolt markings. So grade 2 has no marking, grade 5 has the triangular markings, and so forth. And you can see there's quite a bit of a difference between a grade 2 and a grade 8 bolt. You have a proof strength that's twice the proof load, and so that's seen here. This is an example of some of the metric bolts, and they're in metric units. And again, you see the same thing. One of the lower classes, it's about half the value of one of the higher class strengths. So the proof load can be calculated as Fi, and that's equal to Ki, where this is a constant that ranges typically between 0.75 to 1. If you have a static application, static loading, then you would put Ki to 0.9. If you have an application where you're removing and you have to disassemble and reassemble the bolts, then Ki would be closer to 0.75. And you can look that up in handbooks. But the proof strength is Ki times AT, and that's the stress area from the bolt tables, times SP, which is your proof strength, and that comes from those tables for that bolt. So again, we mentioned earlier, but the applied torque is not, from a torque wrench, is not equal to the torque applied in a bolt. Usually it's off by about plus or minus 30%. And we can use the analysis that we did for power screws to calculate the tension. To calculate the torque that we would need to get to the proof strength. And if we put the coefficient of friction equal to the collar friction, and we say that it's 0.15, goodness gracious, sorry about that. We say that it's equal to 0.15. So, and then we say that the load the load W is equal to the proof strength. We can calculate the torque necessary to get to the proof strength as 0.2 times Fi times D, where D is the bolt diameter. Okay, and keep in mind, we're saying a lot of applications, they'll specify you want to get to this proof strength, so that's how we get to recommended torque values, so that we get to that proof strength. But depending on friction, the actual torque values that are applied from, say, a torque wrench can be off by plus or minus 30%. So another thing to note is that typical bolts and screws lose 5% of their tension a few minutes after they're installed, and they lose another 5% in a few weeks. Another thing to keep in mind is not only do they lose some of their tension right after being installed and a few weeks after being installed, but they're also susceptible to creep at elevated temperatures. Okay, so although we can do the design and come up with good numbers for the bolts, we have to keep in mind these things when we're actually doing design, and make sure that we make machines that have appropriate factors of safety for the environments that they're actually going to be placed in. Along those lines, we have to also think about bolts that are loosening. Okay, so thread loosening, if I could spell, is also a big deal, and that's one of the reasons why we might use rivets and welds, right? So rivets and welds are designed to be permanent, right? And they don't come loose. With vibrations. So when we think about thread loosening, it's important to keep in mind that, you know, a thread is a ramp, and the only thing that's holding these things together is friction. Okay, so to avoid thread loosening, we can do things like add thread lock, or purchase different types of nuts so that we have sufficient friction so they don't work themselves out. Vibration is one of the biggest causes of thread loosening, and what happens is when you have vibration energy, if you think about the block on the plane, and you think about some, you know, vibration energy, all you have to do to get a bolt to work its way off is just slightly get it to move down the ramp, and fasteners often come out off if they don't have the proper thread lock or other form of preventing them from being susceptible to vibration. Another thing to be careful is the for thread loosening is thermal stresses, okay, or different materials with different coefficients of thermal expansion. So if you have different thermal coefficients of thermal expansion, for example, between the threaded surface and the thread on a nut or a bolt or power screw, then you can get stress gradients, which can also cause things to come loose. Surface hardness is a factor. Okay, as well as different surface treatments, and these can be selected so that you maximize the, try to talk and write here, so you maximize that coefficient of friction. All right, so let's turn our attention to bolted joint stiffnesses. And what we're talking about here is taking a look at the effect that the material stiffness has between bolted joints. So let's say we have a bolt here and we have a bolted joint. Let's say we have say a nut here. And we have, let's say, some force. That's an external force on these bolted surfaces. And we want to take a look at what the effect of the stiffness of this material and this material has on the load in the bolt. Okay, so if we take a look at the bottom piece here only, and we balance the forces, then we can say that we have this load in the bolt, and let's say this bolt load is equal to our proof strength, or our proof load, and that we have this load here, which is our clamping load, and we can say it's the clamping load over 2 for distributing it. And this is the case when we have no load. This is an external load, and this is the assembly. And so we can look at what this looks like. We have the external load, so in the presence of an external load, we have this load in the bolt and we have this clamping load. And so what this graphic highlights is that if we have an external load, then either the load FB has to increase to remain in equilibrium, or FC, our clamping force, has to decrease. And this load dynamics, the load dynamics here between the clamping force and the load in the bolt has to do with the relative stiffness of the clamped material. Okay, and we can balance this load if we can say that the external load is equal to the change in the load in the bolt plus the change in load of the clamped member. We can also say that in the presence of an external load that there's going to be some motion delta, or that FE causes delta motion, and we can say that the change in the bolt deflection is equal to the bolt stiffness times delta, and the change in the clamped member force is equal to the stiffness in the clamped member times delta, using Hooke's law. Now both KB and KC are spring constants. And if we collect terms and we plug delta FB in for FB and delta FC in for FB, and then we collect terms and delta, then we can express FE as equal to KB plus KC times delta, which allows us to express then delta in terms of the external load and the stiffnesses in the bolt and clamped members. So what's interesting about this is we can then calculate the changes in the forces in the bolt due to the external load. So then we can say that the change in the force in the bolt is equal to the external load over KB plus KC, and the change in the force in the clamped member is equal to KC times FE over KB plus KC. And so what's interesting about that is that now we have a method of taking a look at the changes in the loads due to an applied force, and that change in the load is due to the relative stiffness of the various members. So if we take a look at what the forces look like as a function of the external load, they look something like this. So as you can see, we have the initial force in the bolt, and this is the line for the force in the bolt. And as the external load is increased, then the load in the clamped member goes down and decreases until you get separation, and then the clamped member force goes to 0, and then the force is totally taken up by the bolt. And if you have an external cyclical load, you can see how the different amplitudes of stress for the bolt and the clamped member look, and this is how fatigue loading is carried through bolted joints. So this is all good, but the question then might be, well, how do we get these stiffnesses? And so if we want to calculate the stiffnesses, we can go back to our statics and look at a member under an axial load, P of length L, with cross-sectional area A and Young's modulus E. And we can also note that the load in a spring is the spring rate times its deflection, or the spring rate is just the load over the deflection. So that allows us to rewrite this as KB is equal to the area of the bolt times the Young's modulus divided by what would be L, but in this case we use G, and G is what's called the grip. And the grip is this length here. If you have a bolt with a nut and the threads here, this is G. that's your length. Then you have KC equal to AC over EC over G. And if you have materials that have, say, K1 and K2, or up to Kn different stiffnesses, we can find an equivalent stiffness using springs in series. 1 over K1 plus 1 over K2 plus however many materials there are, if there's n materials. So then the question becomes, okay, well, that's good, and maybe we understand how to calculate the area of the bolt, maybe, but how do we calculate the area of these plates? Well, it turns out that there's different expressions to do this. A simple method is to use a multiplier and say that that KC is 3 times KB, or to use a different ratio, or to look up in a handbook, or there's some different analytical approaches that we can use that have been recommended by a few different authors. But what they most of them take a look at this area here, and then they find an expression for this zone in terms of the area. The area that is calculated for C in our book, using this case here, is that AC is pi over 4 times D3 plus D2 over 2 squared minus D1 squared. And that comes from an expression here where the nut diameter is D2. The affected zone here is D3, and the diameter of the bolt here is D, and the diameter D1 is the diameter of the hole, the through hole here, D1. And I know this looks a little bit confusing. And then in this case, for small diameters, they say D1 is approximately equal to D. D2 is 1.5 D for hex bolts. These are your standard hex bolts. And that D3 is related to the grip length in D2. So D2 plus G times the tangent of 30 degrees. Or in terms of D, it's 1.5 D plus G tan 30 degrees. So if we work this out, then we can calculate the area for C, and the area for C is approximately equal to, it's supposed to be an approximate sign here, approximately equal to D squared plus 0.68 D times G, where G is the grip, plus 0.065 g squared. Okay, so purpose of showing this is to show that yes, we can get these equivalent stiffnesses. We can get an analytical expression for them, but we've got to get the areas, and there's different people that have worked on different approaches to calculate the area to try to get the bolt stiffness, or we can use some standard joint types. For example, if we have a hex bolts, then we can use this expression. But these are the things where we need to understand the mechanics, understand that there's differences in stiffnesses between the bolt and the clamped member, that there's, when the external load is applied, the load in the clamped member will go down, the load in the bolt will go up until the clamped member separates. And there's handbooks that we can go to investigate the stiffnesses of those joints if we need to.